Hello mathematicians, going to run through some IB AA past questions here, starting from easiest ones, getting on to some very robust and difficult ones. So we see here, starting with a question 4, we know the definition of factorial here. These two numbers at the bottom need to add up to 11, so we know that A needs to equal 2. And my pen needs to work. Why isn't that working now? Oh, it was just pretending. Yes, we know that A equals 2. Incidentally, let's take a little diversion to recall what this means. When we have n choose r, this means we have n factorial over r factorial n minus r factorial. But there are some important results here. If we have n choose 0, that is n factorial over 0 factorial n minus 0 factorial, which simplifies to n factorial. 0 factorial equals 1, and n minus 0 factorial is just n factorial, which equals 1. And that's hopefully makes sense because this is asking how many different ways are there of choosing 0 items from n? Well, there's only one way. You just don't choose any. And this is actually the same as if we have n choose n. Okay, there's a certain symmetry there. You can put the number in the formula, it would just be the other way around on the bottom. How many ways are there of choosing n items from n, where the order doesn't matter? There's only one way. You've just got to choose them all. If we have n choose 1, slightly more complicated, we have n factorial over 1 factorial n minus 1 factorial. Well, let's imagine what that looks like. That's like n minus 1, n minus 2, n minus 3, all the way down. For 1 factorial, we can pretty much disregard. We have n minus 1 times n minus 2, n minus 3, all the way down. And you can see these guys all cancel, and we are left with n. So we have our second important result. N choose 1 is the same as n choose n minus 1, which is n. So for example, if you're asked to do 7 choose 1, we know it's just 7. Because if we're choosing one item from n, it can be any one of those n items. So if we're choosing one item from 7, there are 7 choices. If we're doing n choose n minus 1, we're really choosing one person to leave out, which is the other side of the same coin. The one which is slightly harder is where we have n choose 2. Here we have n factorial over 2 factorial, n minus 2 factorial. By doing the same reasoning as we would do up here, we end up with n minus 1 on top. The n minus 2, n minus 3, n minus 4 all cancel. We're left with 2 factorial on the bottom. So you can imagine if we have to use that in an exam, that's going to be a bit harder. Okay, that is it for the diversion here. Back to the question. We need to find the x9 term. Now, we can consider the general term, which is given to you in your data booklet, which is we have n choose something, and well, in fact, we know that n is 11. So every single term is made up of the binomial coefficient, which is 11 choose something, r being the something corresponding to the number of the term. And then we have the first thing to the power of something, and then we have the second term to 11 minus something. Now, I think in the data booklet, for some reason, it does these the other way around, which I'll do just for this one, but it makes no difference, and I just prefer it the other way. Now, in fact, in this case, I'm not going to do it the other way around because it makes far more sense. We can see that this is just to find x9, it's got to be 9 here, and then to make it up to 11, this needs to be 2, and so we know that r needs to be either 2 or 9. So there's no difficulty in working out what value of r is. Later on, we'll see some where it is a bit harder. So we can evaluate this. I can't remember if this was calculated or not, but 11 choose 2. That's not particularly hard. 2 factorial, 9 factorial, um, times 9 times x 9. So 11, let's look at the bigger number here on the bottom. 11 factorial divided by 9 factorial leaves us with 11 times 10, because then the times 9 times 8 times 7 times 6 all cancels out, divided by 2 times 9 times x to the power of 9. That gives me 11 times 5 times 9, x to the 9 to the 9. That's 45 times 11 is 495 x 9. Make sure we state the coefficient is 495. Okay, hopefully that was a gentle one to get warmed up with. Now this question is quite similar, so I suggest you pause, try it yourself. It's completely similar though. Again, we're considering the general term. So we know it's going to be 7 choose something, x to the power of something, and then k to the power of 7 minus something. And we can see that r needs to be 5. We can see that we've got to have 5 here, 5 here, 2 here. Okay? So straight away we can see this equals 63 x to the power of 5. Again, I can't remember if this was calculated or not, so let's just work this out. 7 factorial over 5 factorial 2 factorial k squared. What we're going to do just here, by the way, we are comparing coefficients. We're not dividing by x to the power of 5, but we know that the number of x to the power of 5s on the left needs to be the same as the number of x to the power of 5s on the right. So we can make this statement here. 7 factorial divided by 5 factorial, that leaves me with 7 times 6 divided by 2 factorial, k squared equals 63. So that's 7 times 3, so it's 21k squared equals 63. K squared equals 3. Possible values of k then are k is plus or minus the square root of 3. On to the next one. Now this is question 6. This is now getting far more robust. So we want to find the value of a constant term of this whole thing. And this, we have a binomial expansion on the right being multiplied by a cubic on the left. So for this to get a constant term, we need the x to the minus 3 term, because then when we multiply it by x to the power of 3, we're going to get x to the power of 0, which is our constant term. Now this can be harder in later questions where we have 2 different ways of getting a constant term. Luckily here, we've only got one way of getting that constant term. So we're going to consider the general term for this thing on the right. So it's going to be 15 choose something, and we've got 1 over 2x to the power of something, and then x squared to the power of 15 minus something. So every single term, when you expand this thing here on the right, can be written like this. So this would give us the different values of r, will give us 16 different terms. And it's not obvious what the value of r needs to be, because we've got some negative powers of x over here, some positive powers of x over here. So we're going to do this a bit more rigorously. There is actually a way of fudging it, but I'm going to go through it a bit more carefully. So what we're going to do is separate the x's from the constant. First term here, and it's quite easy to stuff this up, this needs to be written as a half times x to the minus 1. If you're not convinced as to why that's the case, separate the fraction into a half times 1 over x. You can hopefully see that is the same as 1 over 2x. And that then gives us the same as a half x to the minus 1 to the power of r. Now we can actually expand the power over here. We have 30 minus 2r. We've still got 2 bits of x here, so we're going to keep going. We're going to go 15 choose r. We've got a half the power of r, which I'm going to write as 1 over 2r, and then x to the minus r times x to the 30 minus 2r. We are almost there. 15 choose r, 1 over 2 to the power of r, x to the 30 minus 3r. So every single term from this expansion can be written like this for different values of r. And so we're going to say we want 30 minus 3r to equal negative 3. So we want that x to the minus 3 term. So we have 3r equals 33, r equals 11. And now we can substitute that in. So we've got 15 choose 11, 1 over 2 to the power of 11, and then x to the power of negative 3, which that's exactly how we set this up. I think this would probably be a CAS bit now. So we'll go to here, we type in NCR 15, 11, 1365, and we're dividing that by 2 to the power of 11, which gives us, oh, that's not very nice, is it? 1365 over 2048. So equals 1365 over 2048. So that was our x to the minus 3. Then when we multiply that by this term here, we would get 1365 over 2048. Okay, that was messy. Let us soldier on. Coefficient of the term in x cubed is equal to the coefficient of the term in x5. So once again, we're going to find that general term. So that's going to be 9 choose something, 2x to the power of something, and then k x to the minus 1 to the power of 9 minus something. This is probably the most fundamental skill for these binomial questions. So, whenever you get, if you think you can pause the video and try this yourself now, that would be good. So we have 2 to the power of r, x to the power of r, k to the 9 minus r, x to the r minus 9, which gives me 9 choose r. 2 to the power of r, k to the 9 minus r, x to the 2r minus 9. Now we want the coefficient of x cubed. So for x cubed, we know 2r minus 9 equals 3, r equals 6. So we have, oh, and let's work out the other one as well. For x to the power of 5, we have 2r minus 9 equals 5 plus 9 is 14, r equals 7. So we can say that 9 choose 6, 2 to the power of 6, k to the power of 9 minus 6, which is 3. That is the coefficient of x cubed. That is going to equal 9 choose 7, 2 to the power of 7, k to the power of 9 minus 7, which is 2. Now let's work out 9 choose 6 and 9 choose 7. NCR 9, 6, 9, 7, so that's 84 and 36. So 84 and 36. We can divide both sides by 2 to the power of 6. So we have just 2 left over there. 84k cubed, k squared. We're not going to divide by k squared, tempting as it may be. We're going to shift everything over to one side. We're going to have 84k cubed minus 72k squared equals 0. This is proper maths, okay? Because we're going to end up with some solutions of k equals 0 and then we discard them. But we're not allowed to just solve an equation by dividing by k squared because we would lose potential solutions. We can factorize 12k squared, and that gives 7k minus equals 0. Goodness me, you can hear the wheels turning there. So we have 12k squared equals 0, which is inadmissible, or 7k equals 0, k equals over 7. Let's try number 6. This one is pretty similar. You should be able to try this yourself. Pretty sure it's a calculator question, just looking at the big numbers here. So pause, have a go yourself. Again, we're going to go general term 12 choose something to x to the 4 to the power of r, and then we're going to write 1 over k x squared to the 12 minus r. And sure you get that general term 12 choose r, 2 to the power of r, x to the power of 4r, 1 over k to the 12 minus r, x to the 24 minus 2r. Use r, we've got 2 to the r over k to the 12 minus r. And then when we multiply the x's together, we have 24 plus 2r. Now we want the coefficient of x to the 40 and x to the 38. So x to the 40, 24 plus 2r equals 40, 2r equals 16, r equals 8. X to the 38, 24 plus 2r equals 38, 2r equals 14, r equals 7. We've got to make sure we get the coefficient the right way around. So the coefficient in x to the 40 is going to be 12 choose 8, 2 to the 8 over k to the 4. And we're saying that equals 5 times 12 choose 7 times 2 to the 7 k to the 5. Okay, let's evaluate 12 choose 8, 12 choose 7. The R 12 choose 8, 495 and 792. So 495 and 792 to 8 over k 4 times 2 to the 7 over k to the 5. At this point, I mean, we probably could just end solve it, but let's be um, purists about this. We can divide by 2 to the 7 on both sides, giving us just 2 there. And then if we do 495 times 2, that is 990. We're going to cross multiply, so that's going to be 990k5, 5 times 792, 3960k4. So what I've done there to explain cross multiplying, I've multiplied both sides by k to the 5 and k to the 4. Possibly overkill, but whatever. Take everything to one side. Minus 3960k4 equals 0. I guess we could divide by 10, couldn't we? I mean, at this point, really. We'll just go k 90. Sorry, k to the 4, 99 k minus 396 equals 0. So k4 equals 0. Inadmissible. 99k equals 396. K equals 396 over 99, which equals is just 4. When you get an answer like that, you feel like, yep, there's no way that's wrong. Onwards and upwards to yet another cliche, I suppose. Okay, question like this, have a bit of a sinking feeling and go, oh, really? What's going on? And we just have to be a little bit brave, get into it, and write down the general term. So we'll go n choose something, x squared the power of something, and then 1.2 to the n minus something. Ugh. However, the good thing is that we know that r equals 3 here. So we can see that to get x to the power of 6, there's only one x term in the bracket. So we can see it's really n choose 3, x to the 2 to the 3, which is x to the 6, times 1.2 to the n minus 3. So the coefficient of this term is n choose 3, 1.2 n minus 3, and we know that that needs to be greater than 200,000. Now, the term here on the n choose 3, I mean, we could probably ban that if we had to. I suspect our calculator will let us get away with it, but let's just do this anyway. 3 factorial n minus 3 factorial times 1.2 n minus 3 equal, if we imagine expanding the whole top, n minus 1, n minus 2, n minus 3, we would end up with n minus 1, n minus 2, then with the n minus 3 all the way down cancelling, divided by 3 factorial, which is 6 times 1.2 to the n minus 3. And that is the thing we want to be greater than 200,000. So let's go insert problem for a new problem, add a graph, and type in that monster of an expression. So it was x, make sure we put the times in there, x minus 1 times x minus 2 divided by 6. Oops. What am I doing wrong there? Why isn't that? There we go, divided by 6 times 1.2 to the power of n minus 3. Oh, and that means I did something wrong, doesn't it? I typed in n when I should have been typing in x the whole way through. Oh dear, I have to do that again. X times x minus 1 times minus 2 divided by 6 times 1.2 to the power of x minus 3. Now we know we want this to go up 200,000, so let's play around with the um, window a little bit. We'll go menu, window, settings. Let's take the y up to 200. Num 201,000. Let's see, that's not giving us enough on the X. What you're thinking, well, why don't you just do this in nsol? I'm thinking the same thing, but it's fun to play around with the windows sometime. Okay, this looks about right. So we'll now type in 200,000. That is a line just up there. You probably can't see. Let's just window settings. Let's go 210,000. There we go. So we're looking to find this point of intersection up here. We go to menu, analyze graph, intersection, and we have 26.5, which means our value of n is going to need to be 27, because we need to round up. We could just as well have gone nsol. Let's see if it would have worked with just the original ncr n choose 3 times 1.2 to the power of n minus 3 equals 200,000, solving for n. That's seem too terrible. Oh, n2, comma 3. That's what it is. Oh, and actually, that works. So we didn't need to worry about the algebraic expansion in this case. We could have put ncr in the function. And we get 26 point something. So we would need to give our answer for n as 27. Last question. Always tempted not to do it. It feels like a bit of an anticlimax after that one. And it seems annoying the way they've got n plus 1 here. We'll try and just work with their n plus 1. But if you decided to say, well, let's call it 3 plus x squared to the power of m, and then say where m equals n plus 1, that would be absolutely fine. In fact, that's what I'm going to do. That seems so much nicer. So, looking for the squared term, so we have m choose something x squared to the something 3 to the m minus something. And again, here we can see that the r needs to be 2, so it's going to be m choose 2, x to the 2 to the power of 2, which is 4, and then 3 to the m minus 2, that r equals 2. And we know that m choose 2, 3 to the m minus 2 equals 20412. Now I mentioned we can expand this, and if this was a non-calculator paper, we might have to. And it works out, have a quick go, pausing if it's not too late, over 2 times 3 to the m minus 2 equals that thing, which we're just going to solve using the calculator. And so, where are we? Menu, 3, and solve. I have to do the same thing, ncr m comma 2 times 3 m minus 2 equals 20412. Solving that for m, we have 8. So we have m equals 8. So 8 equals n plus 1. N equals 7. That's everything. Hope you've enjoyed this collection of increasingly difficult binomial questions.